Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Laurent Massouli from the MSR INRIA Center in Paris, who will tell us about community detection thresholds.
Thank you, Yuval. It's a pleasure for me to be able to give you this talk this morning. What is it about? Community detection is basically the same as clustering. It's about identifying groups of objects with similar characteristics from within a global population, and so embedding is also a closely related objective. You may want to embed your individuals within a space and then do clustering after having performed embedding. And so if I had to state one application, then I would say this is a useful primitive, for instance, for recommending contacts in online social networks. You might process the friendship graph and then recommend users to connect to people that constitute their implicit community. So much for motivation. Here's another one, but I'll not dwell on it. So the main character in this talk will be the stochastic block model. So it's a random graph model whereby we have n nodes, n being large, and each node belongs to some community. Specifically, we sample in an IID fashion spins for each of the nodes. So each node might pick a type out of k different types in an IID fashion. And then conditional on those spins, we decide independently to create an edge between two nodes with a probability that depends on the underlying types. And so B is this probability. That's a function of the types of the two n nodes, sigma u, sigma v. But then this is scaled by S over n, where n is the population size, and S should be thought of as the signal strength in the observation. It's pretty much the average degree of the graph. It gives you the scale of the average degree in the graph. And so what we observe is this random graph that is a realization from the stochastic block model, and we'd like to recover the underlying communities as much as possible. Before I say a bit more precisely what I want to cover within the talk, let me recall what spectral clustering in its classical version is. It's just the fact of processing this adjacency matrix, extracting the eigenvectors corresponding to the largest eigenvalues, and then you do an embedding using these eigenvectors, having normalized them. If you pick R eigenvectors, you can embed the nodes in R-dimensional Euclidean space, and then you could do, say, k-means clustering or whatnot on the basis of this. And so what I really want to tell you about today is about a phase transition that occurs when you want to do inference about these underlying communities, when we have a very sparse graph that we observe, so order 1 average degree. But before getting to that, I will do a detour and say a few things about the case where we have a little more edges to work with, because this will help me introduce some notions of spectral separation, which will be helpful in understanding the remainder. So let's assume to start with that we have what I call a rich signal, that is the average degree parameter S is at least logarithmic in the system size. And so in that case, modulo an assumption that you could distinguish the different clusters, that they are statistically distinct, which is not really a big deal, because if they are not, then they should be considered as the same cluster. So then classical spectral clustering will work essentially because the spectrum of the matrix A will consist in a small number of eigenvalues that stand out, So their number is going to be less than the number of the underlying communities. The magnitude of the eigenvalues will be order S, at least, and the remainder will be negligible. It will be on the order of square root of S. And so, in principle, by putting up a threshold, you could extract the right eigenvalues, do the embedding, and moreover, what is true in this regime is that the representatives of the nodes in this embedding will cluster according to the underlying communities, except perhaps for vanishingly small fraction of the nodes. So here's a simulation of this, this setup with 4 blocks, and well, n is not going to infinity here, so we have some scattering around where they are supposed, the node representatives are supposed to cluster, but still you see the phenomenon starting to emerge. And so let me say a few words about why this holds. So recall that the adjacency matrix that we are going to work with is can be decomposed into its expectation, which has this nice block structure and which has low rank on the order of the number of blocks, and the eigenvalues on the order of the signal strength S. And then after centering A, you create this random matrix that you would add to this expected value matrix. And so what we want to leverage is some kind of spectral separation, essentially saying that the random noise matrix has a very small spectral radius, which will entail that the spectral structure of the perturbed matrix is very close to that of the unperturbed matrix. So the prototype for this spectral separation is this so-called Ramanujan property, which is something that was introduced in the 80s by Lubotsky et al., which essentially is defined for S-regular graphs, and which says that the second largest eigenvalue ought to be as small as possible, and that is on the order of the square root of S. So that's the definition of a Ramanujan graph. And we know by Friedman's work in 2008 that a random S-regular graph with high probability is almost Ramanujan in that the second largest eigenvalue is close to the bound in the definition of those Ramanujan graphs. But what we need to establish what I just described is something else on Erdős-Renyi graphs this time, so not necessarily regular graphs. And Feige and Ofek in 2005 established similar property. So long as the degree now is at least logarithmic, we still have this behavior that the second largest eigenvalue of an Erdős-Renyi graph's adjacency matrix is on the order of the square root of the average degree. And related result is that if you center this adjacency matrix, then you have a perturbation matrix whose spectral radius is also on the order of the square root of the average degree. So these are all relaxations of the original Ramanujan graph definition. So you could say you have almost Ramanujan graphs, somewhat Ramanujan graphs, and we'll see further weakenings of this definition that will be useful for our purpose. So with this result in hand, you can go back to the stochastic block model, consider the adjacency matrix after centering, and using Feige and Ofek, you can show that it has a spectral radius on the order of the square root of the signal strength. And this is of a lower order of the leading eigenvalues of the expected adjacency matrix. So we can indeed say that the spectral structure of the adjacency matrix is close to that of the expected adjacency matrix. But what we can say also is that if we let the signal strength go down, then this breaks down, because we know that the spectral radius of the noise matrix will be dominated by the largest degrees, And for order 1 degrees, this is on, well, this spectral radius will be on the order of the square root of log n over log n, whereas we may have S as low as 1. So we know that classical spectral clustering has to break down for signal strength on the order of log n over log n. But we may still do other things than classical spectral clustering, and this is what I want to get to, focusing now on weak signal strength and on an interesting phase transition phenomenon in that regime. So let's now assume that signal strength is of order 1. We know then that we cannot correctly recover the underlying clusters because we will have isolated nodes, for instance, and there's no way we can tell which community an isolated node belongs to. So we have to set up for a less ambitious objective. And so the objective will be then to achieve a good overlap, so guess community labels and make sure that the agreement between the estimated labels with the true underlying labels is as large as possible. And this is what this overlap metric measures. It counts the number of nodes for which we guessed right, and there is an offset that is removed to take into account the fact that you could assign to each node the same type, and that would not be meaningful. Anyhow, so with this definition at hand, what you might expect is that as you reduce the signal strength, then the best you can do is to achieve some positive overlap that is not 1, but slightly less than 1, but that decreases continuously until the point where you don't have a giant component anymore. So that would be the naive guess. But it turns out that something more interesting happens. You have a transition point prior to the disappearance of the giant component, where the overlap has to be 0, below which the overlap has to be 0, and still you have a giant component. So this is this intermediate phase between the signal strength S0 and SC I'm illustrating here. So this is what I want to look at now. And specializing further now on the simplest non-trivial community stochastic block model that you can imagine. That is 2 communities, roughly equal sizes. So the spins now are plus or minus signs. And we have just 2 parameters. The parameter A characterizes the probability of an internal edge within a community. So this probability would be A over n. And then you'd have a second parameter B, which characterizes the probability of an inter-community edge, which would then be B over n. And so in that context, physicists, Decelle et al. In 2011, made a conjecture that there would be a threshold tau depending on the parameters A and B, such that for tau less than 1, the overlap has to be 0. So you cannot make any meaningful inference about the underlying communities. The signal is simply not useful to that end. And so this part of the conjecture was proven in 2012 by Mossel, Neeman, and Sly. And the other half of the conjecture made by Decelle et al. Was that if this tau parameter is above 1, then positive overlap can be achieved. And in their original paper, they said that it could be achieved using belief propagation, so message passing algorithms, and they have numerical evidence that indeed this is the case. And there is a more recent conjecture by Decelle et al. As well as Mossel, Neeman, and Sly. So this is KMM, NSZ, and Zhang, the 2013 paper, where they come up with a spectral algorithm, which they call the spectral redemption. And they conjecture that this one can achieve positive overlap when tau is larger than 1. But until November 2013, there was no proof that indeed the positive part of the conjecture held. But now we are in a much better state of affairs because we have 2 proofs. So I came up with one, and then a a week later, Mossel, Neeman, and Sly posted yet another proof. So we have plenty of proofs with two different methods to achieve positive overlap above the transition point. So let me now tell you how this proof works and what is the method used to achieve positive overlap above the transition point. So this is going to be done using a modified spectral method, and the key is to introduce the right matrix on which we want to do spectral clustering. We are no longer working directly with the original adjacency matrix, but instead we're constructing a matrix which counts adjacency at a distance somehow. And more precisely, I take a path length parameter L, and for each pair of nodes I and j, I count the number of self-avoiding paths in the graph between I and j. So this is what this matrix B is about. And the typical situation is that for a node I would have a tree-like local neighborhood, in which case BLIJ would be 1 only if the graph distance is precisely L between nodes I and j. This is the typical case. But if we have cycles, then it might be different. For instance, the second case here, you may have two self-avoiding walks of distance L between I and j, and you may ignore the third case for now. So the main result is about the spectral structure of this matrix, which then implies that we can do some clustering and achieve a positive overlap. So if we pick the path length to be logarithmic in the system size, then the spectral structure of this matrix is such that there is a leading eigenvector whose there's a leading eigenvalue, of the order alpha to the L, where alpha is the average degree in this graph, A plus B over 2. There's a second eigenvalue which is on the order of beta raised to the L, where beta is another key parameter in this model. This is A minus B over 2. And we know also that the corresponding eigenvectors are aligned with vectors we know quite well. For the first eigenvalue, the eigenvector is aligned with the vector obtained by applying the all ones vector to this matrix B. And in the second, for the second eigenvalue, the eigenvector is aligned with the vector obtained by applying the spin vector to this matrix B. And we have a third and remaining eigenvectors, which are O of essentially a square root of alpha to the L. So, yes?
So what is the dependence on the small c that you choose in L? So L is some c times log n. So this is true for...
I need c to be positive, but I also need alpha to the c to be less than 1/4. So there is a constraint on c here, which has to do with the presence of cycles in the neighborhoods of the nodes. But that's the range of parameter values for c that I can cope with. And so the fact that the third eigenvalue up to the n to the epsilon for an arbitrary positive epsilon is of the order of the square root of the first is what I call a weak Ramanujan property. And so the final statement in the main result is that the second eigenvector correlates with the underlying communities. So I can do thresholding on this second eigenvector, and I will achieve my community detection. All right. So what I want to do in the remainder of the talk is describe the key ingredient in the proof and then conclude. So, and this is just an illustration that it seems to work in practice. So I tried it out, and so here you should see the overlap become positive. It's not completely obvious. Maybe I should do more simulations to confirm the theory, but it does not disprove it, at least.
Confirm the simulation.
Yes. So the key step is to introduce a matrix expansion expression. So in order to do that, what I'm introducing here is the expectation of the adjacency matrix conditional on the spins. So it's a simple matrix with essentially rank 2 if you ignore the diagonal terms. But so this can be expressed in terms of the all ones vector and the vector of spins in this way. And based on this, it's useful to introduce now what I call a centered path adjacency matrix, which is essentially constructed as the matrix B was from the original adjacency matrix, but it's now constructed from the centered adjacency matrix. So the ij entry is just the sum over self-avoiding walks between I and j of the products of these terms, right? And so once I have this at hand, I can write an expansion. So I can consider this and say, well, I'll expand those products and group terms according to the place at which the last A-bar product appears. And what you see by doing that is that after this last A-bar product term appears, you'll have only A terms. And since you are considering self-avoiding paths here, you will have essentially terms that correspond more or less to the matrix B, but to corresponding to a shorter path length. So you essentially find that your matrix B is this perturbation matrix plus some expansion which involves the matrix B with lower indices and perturbation matrices with lower indices. So this is the first step, and this is crucial because we can do some work on this delta matrix, whereas working directly with the B matrix is hard. And so indeed we can use classical tools for controlling spectral radii of random matrices to control this delta matrix. And basically we can use this trace method. So we can look at the trace of the matrix raised to some power, and by combinatorial arguments, actually leveraging Furedi and Komlos's work in the 80s, I think. So there's a paper by Furedi and Komlos which does this kind of control. We throw in the additional ingredient that we are considering self-avoiding paths, and this gives us some control on the spectral radius in the end. And essentially what we have is that this perturbation matrix has a spectral radius ignoring the first term that is on the order of the square root of the degree raised to the L. So this is one key ingredient in there. And then the second ingredient is what you could think of as a local analysis. You just need now to work with the local structure of the neighborhoods in this graph. And so the ingredient here is to show that if you look at the sizes of the neighborhoods at distance t, as well as the sums of spins at distance t, this has some kind of a quasi-deterministic growth pattern. And this is what is written here in red. So that's the number of neighbors at distance t. This is roughly the number at distance L scaled by a constant plus some perturbation, and similarly for the sum of spins. And so from this you can, so this is an intermediate step. I'm nearly done. So I'll put that together with the control of the spectral radius on the next slide. So now if you look at the supremum of norm 1 vectors, which are orthogonal to the candidate eigenvectors, BL E and BL sigma, applied to B raised to some m minus 1 and here the E vector, then you can control that. You get a square root n term, but you get also an alpha to the m over 2 term. And the reason why this holds is that these vectors here are in a precise sense, close to the vectors of sizes of neighborhoods and spin sums at given distances. And so if you force X to be orthogonal to these two things, then it will be orthogonal to the first terms in here. So you will be left with the perturbation terms here only. And so putting everything together now, we can show that if we restrict ourselves to unit vectors orthogonal to the candidate eigenvectors, then BL times X has a norm that is on the order that we are interested in, that is on the order of the square root of the average degree raised to the L. And basically, this is a combination of the ingredients I've just given. So the expansion, the controls on the spectral radii of the coefficients in the expansion, and this last fact. So just putting it all together gives the result. And the rest is much easier. This is the most non-obvious step, I think, in this proof. And you can conclude by leveraging Courant-Fisher theorem and controlling the norms of the candidate eigenvectors applied to this B matrix. And this allows to conclude about the spectral structure. And there is more work to be done in order to show that the second eigenvector correlates positively with the underlying community structure. But this is again a local analysis working on the local neighborhoods of nodes, characterizing how they behave, relating this to a random tree model that is the natural model for those neighborhoods. So I'm done, and let me conclude now and mention some outlook. So I mean, the key message is that you can recover this Ramanujan-like spectral separation by using these kinds of spectral of path expansion techniques, working with this matrix B rather than with the original adjacency matrix. And so this may have consequences beyond this highly stylized model. For instance, we have a generalization of the conjecture when we have a model with not just spins, but also labels on the edges, which is something we introduced motivated by the Netflix prize dataset, where the edges would be between a movie and a user, and they would be labeled with a number of stars that the user gave as a rating to that movie. So we have a generalization of this threshold phenomenon for those labeled stochastic block models, and it needs to be work needs to be done to see if we can generalize this path expansion to prove this generalized conjecture, and also this technique may be used to prove the other conjecture made more recently by the KMM-NSZZ paper. So I have not said what spectral redemption is, but I can say in a nutshell. So the way they propose to identify the communities is to form an edge-to-edge matrix, and you would connect an edge to another edge in this matrix if they have a common endpoint, but you forbid. So these are oriented edges, and so the head of the input edge should be the tail of the output edge, and you prevent backtracking, so you cannot go back along an edge. So this defines an edge-to-edge matrix. And so their conjecture is that above the threshold, it has one second eigenvalue that stands out and whose eigenvector can be leveraged similarly as what I've been describing. So there is hope that we could use the same method that I used with the matrix expansion and the trace bound to establish this. And then there are a bunch of questions like I'm not entirely sure that stochastic block models are a good model for all the applications I just briefly mentioned. So I would be interested in knowing whether this is the case. For one thing, you certainly need to allow more flexibility, like allowing general degree distributions, which Fan Chung has done to some extent in a recent paper with Kamalika Chowdhury. But still, it's not clear. It's a good model for the data we are interested in. And then there are plenty of other questions, the speed of convergence, the embedding dimension, and so forth. So with this, I will stop. And here are the references. So this is the paper with the results I was describing. And here is the other proof that is available of this conjecture by Mossel, Neeman, and Sly. Thank you.
Questions?
So are there similar models for the regular regime? So you can define some block. So is there some block model on a regular graph, and are there similar questions that can be answered?
Yes, you can.
Where you don't have this independence of occurrence of agent.
So for instance, you could have some versions of the configuration model. So you could sample, fix the degrees, sample the number of edges that are intra and inter. And there may be different models for doing that. This could be done on independently throwing coins to determine that. And then once you have decided which edges are intra and inter, you do a random matching of these half edges. Here there may not be this intermediate phase because the regularity may help. But I'm not entirely sure. Yuval seems to be skeptical that there would not be such an intermediate phase.
I mean, I haven't worked on this, but my guess is that there would be an intermediate phase as well. It'd be interesting to
So there is one version where you say each node will have 3 neighbors, internal and 2 external. And for this one, I think maybe there is no such intermediate phase. If you randomize, maybe it makes this intermediate phase appear. Another thing which we have been thinking is what could be said when you have more than 2 communities. Because as you increase the number of communities, things become even more interesting. So there is something happening when you have 5 or more communities where you have a phase where the physicists tell us below a transition point, all spectral methods will fail, but still some non-polynomial methods should work. And so we could try to prove that we have spectral methods working all the way up to that point. So these things are better understood in the case of the reconstruction on a tree, on which Yuval has done lots of very interesting works. So translating what is known on the trees onto the stochastic block model is already a challenge, and this intermediate phase is quite a mystery.
So is there any magic number 5? So is it specifically 5, or is it just for 5 it's sort of known, and for 4 you don't really know what?
I think for up to 4 included, this additional phase does not exist, at least for the symmetric situation where you have, let's say, 4 communities, 2 parameters A and B for intra and inter edges. Then there would not be such an additional phase.
Works only for 2 communities, or your result holds only for 2 communities, or for 3, 4 it is also?
So right now it's written for 2. I'm confident that it could be extended, but I have not done that, so I'll be cautious.
I mean, even in the case of trees, there was a big gap between the case of 2 and 3. So the number of colors, even from 2 to 3, it turned out that the spectral methods were sharp, but it was kind of much easier for 2 than for 3. So, and then the fact that they break down at 5 is fascinating, and it should have an analog here.
Yes, yes. So, discussing with Lenka Zdeborova, who's one of the authors of the original conjecture, she tells me she thinks this will have an analog, and in this hard range, no polynomial time algorithm should be able to achieve positive overlap, whereas maximum likelihood would somehow. But I don't know what is the basis for this guess that they are making.
I would believe it at the level that maximum likelihood would, and kind of no spectral algorithm, but to generalize to all polynomial is another leap.
Yes, yes, I guess this has to do.
Sophisticated polynomial.
Yes, I asked her, and I guess it has to do with the work on the energy landscape that they have been doing on I forget the name, but there was an attempt to make message passing work even beyond the known limit, and they came up with a survey propagation method, and so they developed an understanding of the attractors of those iterative schemes. So I guess this comes from there, but anyhow.
Okay. Thank you, Ramanujan.
Thank you.